Okay, page 3 of the Newton's Laws test review. So we have a couple of cars. You're supposed to label the arrows with their names. So we're supposed to draw arrows for the forces acting on this car. This is the acceleration phase. This is the deceleration phase. The way this car works is this arm is pulled forward. There's a spring in there. That pulls the string like this, and the string unwinds a wheel. So, use arrows to show all the forces acting on the car. During this, we have the force of the motor, which is the spring in here. You could also call it the spring. And opposing that, we have the force of friction. In this picture, we just have the force of friction. I think that's it. Now, if I wanted to make this really accurate, I'd make the motor arrow bigger because it's more powerful than friction, assuming that the car is actually going to move. But it must be moving, otherwise there would be no friction. Alright, that was kind of a lame question. Number 31, you cannot throw a feather with as much force as you can throw a desk. What could you do to prove this? Which of Newton's laws do you need to use in your proof? So what you would do is, push a feather away as fast as you can. Then do the same with a desk. When you do this, the desk is going to push you back. You're going to find yourself, if I pushed this desk away as fast as I could, that would push me backward. If I pushed a feather away as fast as I could, it wouldn't push me backward. So I'm going to write, only the desk will push you back. So the desk pushed you with a stronger force. So you must have pushed the desk with a stronger force. And I've messed up the next problem. Didn't leave you enough space on this. Which of Newton's laws is this? This is Newton's third law, which says every action has an equal and opposite reaction. So when you push a feather, you're pushing the feather's pushing you. The forces are exactly the same. The force of you pushing the feather and the force of the feather pushing you. The feather doesn't push you back very much, which means you didn't push it very hard. Neither one of you pushed very hard. When you push the desk, it pushes you back, which says you must have pushed it pretty hard too. Newton's third law is the one that tells us this. Number 32, the mousetrap car on the right moves when the spring lifts the arm upward. Which way is the car going to move? So if this string goes upward, the string is on the right side of this axle. That's going to make this axle rotate to our left, and the car is going to go leftward. The whole thing is going to rotate like that, and the car is going to go this way. So I'm going to write leftward. Use Newton's third law to explain why this happens. Well, it happens right here. This is where the wheel pushes the road to the right. And when the wheel pushes the road to the right, the road pushes the wheel to the left. Wheel pushes road to right, road pushes wheel to left. Diagram on the right shows a ball falling from the sky. This is before it reaches terminal velocity. It's fallen down, it gets to terminal velocity right here, and this is after it's reached terminal velocity. Terminal velocity is the point at which the ball no longer accelerates. It's the point at which the force of air resistance pushing up is equal to the force of weight pushing down. When it's right here, I'll just draw some arrows. The air resistance is weaker than the weight. Let me redraw that. I'm going to make this arrow smaller so it's really obvious. When it gets down here to terminal velocity, then the air it's going fast enough that now the air is pushing stronger, and that air is pushing just as strong as the weight is pushing it down. So in this case, there's a net force downward. That means the ball gets faster and faster and faster. It's accelerating downward. When it gets to here, there's no net force anymore, so it's still going to keep moving in a straight line at a constant speed, but it will not accelerate. Number 33. Circle all that are true for this one before it reaches terminal velocity. Weight is greater than air resistance. That is true. B. Air resistance is greater than weight? No. Air resistance equals weight? No. Net force is downward? Yes. This is stronger than that, so there's a downward net force. Net force is upward? No. 34. Circle all that are true after the ball is at terminal velocity. So we're looking at this one now. Weight is greater than air resistance? No, they're the same. Air is greater than weight? Nope, same. C. Air resistance equals weight? Yes. Net force downward, net force upward? No, there's no net force. Okay. Number 35 through 36. For the bicycle and the SUV on the right, draw and label a vector representing the net force. Then tell whether the object is accelerating, decelerating, or moving at a constant speed. This is kind of hard to see. Let me zoom in a little bit on this. Yeah, I don't know. Still may be fuzzy. So there's the baseball's or the bicycle is moving down the hill, and there's a 40 Newton force pushing it up the hill, a 20 Newton force pushing it down. So the net force is, this one's going to win. The net force is going to be 20 Newtons up the hill, like that. So since the bike is going downhill, and the net force is pushing it uphill, the net force is opposite its motion. It's going to slow it down. So this is decelerating. I'm going to put a little label like that. Decelerating. Slowing down. Now in this case, there's a 30 Newton force to the right, 30 Newton force to the left. The net force is 0 newtons. So I don't need an arrow. It's balanced. That means this car is not accelerating, it's not decelerating, it's moving at a constant speed. Alright, similar kinds of problems. Let me zoom out though. Here we've got to fill in the blanks. So, we have a person with a mass of 50 kilograms, accelerating 4 meters per second squared. The net force is going to be determined by Newton's second law, mass times acceleration. Mass of 50 kilograms multiplied by 4 meters per second squared. We get, multiply 50 times 4, and I get 200 newtons. So that's the net force. I'm going to add that in now. The net force, and it's positive, so that means there's a net force to the right of 200 newtons. What I see here is an 80 Newton force of wind to the left. Now my net force tells me which of the forces is stronger, the one taking it this way, the muscle, or the one taking it that way, the wind. And since the arrow is going to the right, I know that muscle is stronger. And this number tells us how much stronger it is. The muscle is 200 newtons more than the wind. To figure what number is 200 newtons more than the wind, we add them together and you get 280. That's the force of the muscle. It's 200 newtons more than the wind. Now for this one, use the same formula, F equals ma. Mass is 100 kilograms. The acceleration is -3 meters per second squared. So the net force is -300 newtons. -300 newtons. That means to the left. The negative means to the left. I'm not going to put the negative in the diagram. I'm just going to draw an arrow to the left. You can either write a negative or you can use an arrow going left. But don't do both. Otherwise it looks like -300 to the left, which actually means 300 to the right. So in this case, this tells us that the wind is stronger. And it tells us that the wind is stronger by 300 newtons. So if the wind is 500, and that's 300 newtons stronger than the muscle, we need to find something that's 300 newtons less than 500. And that's going to be 200. 500 minus 300 is 200. So over here we added, here we subtract. There's a good reason that we did it. Just watch this again if you don't remember the reasoning. So 500 is 300 newtons more than 200. 39 through 42, the ice skaters. This is before, this is after. They're standing on this frictionless ice. Somebody pushes somebody else, and this person is 200 kilograms. That's a big ice skater. 100 kilograms, that's a big ice skater, but this is really big. Who moves faster after they push away? Well, Newton's third law says the action and reaction are the same. So this person pushes that person pushes this person, the forces are the same. And with the same force, a bigger person is going to be slower. So who moves faster? It's the 100 kilogram person. This is faster. How do you know? I'm going to say same force accelerates, well, same force, I'm just going to put a period there, same force, so they have the same force is pushing each one. 100 kilogram person has less inertia, so motion changes more easily. That's one way to explain it. Who gets pushed with more force? Neither. Same force. Newton's third law says the forces have to be equal and opposite. For 42, if the 100 kilogram skater accelerates at a rate of -4 meters per second squared, how fast will the 200 kilogram skater accelerate? That's saying this is 4 meters per second squared to the left. The bigger person, who's twice as massive, is probably going to accelerate half that fast to the right. So 2 meters per second squared. 43, two cars collide head-on. This is a 2,000 kilogram car. This is a 1,000 kilogram car. They crash into one another. They hit. When they collide, they stick together. Which car's velocity changes more? Well, the 1,000 kilogram car. And its velocity changes more because it has less inertia. Inertia, remember, is resistance to change. Resistance to change in motion. And the more mass you have, the more inertia you have. So this is going to keep doing what it's doing. Its motion is going to stay the same. This one's motion is going to get changed more. I'll stop there and just do the last one as a single.